And then I can share it with you guys in case you wish to go back to it. Okay, so today we're going to pick up in Module 2, and the topic of discussion is going to be the binomial distribution. This is a kind of a new topic that we have just recently added to the course. But before we actually get into that lesson, I want to kind of give you an overview about this particular topic. And I am going to utilize the PowerPoint that's in D2L. I hadn't been doing that too much this semester, and that's fine. I can give you a quick summary, but this is a real short, quick video, or not video, but a PowerPoint, and it will be easier to do it that way. I just got to log in. The PowerPoint is actually under the lesson probability and contingency tables, which we talked about last week. And it's entitled the Probability Distribution Overview. And so I want to kind of look at that overview first. We've been talking about, most recently, we've been talking about frequency distributions. At the end of Module 1, we talked about categorical frequency distributions, which allowed us to organize the qualitative data into a table format. Remember, frequency distribution is the fancy language in statistics for a table. We also talked about how to create a grouped frequency distribution at the beginning of Module 2 with quantitative data. And the thing behind, or the idea behind a frequency distribution, is we're taking the raw data, the data that we really went out and collected, and organizing it into a table. So a frequency distribution gives us an idea of the reality. It's like what really happened. So it's our reality. And we also talked about previously that frequency distribution is kind of a jump start to some of the graphs we create, whether it's a bar graph, a circle graph for qualitative data, or the histogram and the box plot for quantitative data. But again, the idea behind the frequency distribution is it's going to show you what really happened. It's your reality. Today, we're going to begin talking about probability distributions. Probability distributions, it's still a fancy term for a table, okay? But it changes its focus. Instead of focusing on the frequency of a category or the frequency of a particular number range, it focuses on the probability of that particular event occurring. One that would be very simple, if you want to think about it, that you would probably be familiar with, would be the idea of if you planned to flip a coin. They kind of call that our experiment. Okay, and when you flip a coin, if you think about it, you're either going to get a head or you're going to get a tail. And most of us know that the probability of a head is that 0.5, 1 out of 2, or 50%, depending on how you wish to write it. And similarly, it's also 0.5 for or 1/2 or 50% for a tail. And so that little table there with that simple example is a probability distribution. it tells us what should happen if everything works the way it's supposed to. Okay? And there are different types of probability distributions. And we're going to look at a few of each type. Okay, so the difference is the frequency distribution is your reality. It tells you what really happened. A probability distribution is going to tell you what should, if everything worked the way it's supposed to, happen based on the probability. Now, I showed it to you in table form, but just like with a frequency distribution, it can also be displayed as a graph. And we can even use a formula. We don't worry too much about the formulas in this class, okay? But there exists a calculus-based statistics. And if you were in a calculus-based statistics course, then you would use the formulas and perform calculus techniques to solve the problems. Okay, so you don't have to worry about that because we're not in a calculus-based class. But there are two categories of probability distributions. And quite honestly, they should sound familiar to you. The first category is a discrete probability distribution. You'll remember when we talked about data, specifically quantitative data, we had discrete and continuous. And so discrete probability distributions is kind of that carryover from the type of data. Discrete, remember, means you have a countable number of outcomes. Like when we flip a coin, we know there's two things that can happen. When we roll a die, that six-sided cube, we know there are 6 things that can happen. If we're talking about doing something with cards, with a standard deck of cards, there's 52 cards in the deck. So there are 52 possible things that can happen. So a discrete probability distribution has a countable number of outcomes. And again, typically those are, remember, whole numbers. 2, 6, 52. The probabilities are typically based on theory. The idea of flipping a coin. We know there's one way to get ahead out of 2 things. Sometimes it can be based on experiments or a lot of research, years of collecting data. But typically, again, it's determined theoretically or by observation. We can create a table. Well, you can also create graphs. The 2 key things, and it's really 2 probability rules that we learned earlier on about probability that carry over to that probability distribution. We know that all probabilities have to be between 0 and 1. Can't be negative. And it's not going to be greater than 1. Never, ever. Okay? And then the sum of the probabilities of all the different things that can happen total to 1. Because remember, the probability of 1 means something's going to happen. For sure. Remember, that's the probability of something being certain, going to happen regardless of what you do. And so I can kind of show that to you with our example here of flipping a coin. 0.5 is between 0 and 1. 0.5 again is between 0 and 1. And if we add those up, because those are the only 2 things that can happen, I hope you realize that 0.5 plus 0.5 is 1 whole, or 1/2 plus 1/2 is a whole, or 50% and 50% make 100%. Okay, so we have discrete, which again are typically based on discrete data. The second category is the continuous. Just like we had quantitative continuous data, we also have continuous probability distributions. And again, the idea of it being continuous is it is on that continuum. And we can break it down into smaller and smaller units. These particular probabilities are determined theoretically, typically by an experiment of thousands or hundreds of thousands of times of conducting the event. Again, we can create a table or a graph. Oftentimes with continuous, we deal with a graph more so than a table. Discrete, we usually deal with a table. Continuous, we deal with a graph. And the two requirements are very similar. And when we get there, I'll show it to you. Okay, I'm not going to show it to you today. But the two requirements for a continuous probability distribution is that the total area under the, quote, curve is 1. And the probability of each outcome is between or equal to 0 and 1. You still have that same rule that all probabilities are between 0 and 1. But because we're looking at it graphically, we have to think about the area under the curve. And so that's a little bit different. But when we get to continuous probability distributions next week, next Monday, I'll show it to you. Okay, so just hold on for the ride. Our focus today is going to be on the discrete probability distributions. Now, there are a variety of discrete probability distributions as well as continuous probability distributions. I've put some of the more popular ones that are used within statistics. It's not an exhaustive list, okay? So there are others, but these are the ones that are used most often. Discrete, we can talk about the binomial, the Poisson, and the hypergeometric. Our focus in this course is the binomial. Now, should you choose to take the next statistics course, which is Math 2401, you get to talk about Poisson and hypergeometric. Similarly, with the continuous probability distribution, there are a variety, and we'll actually touch on all 4 of these by the end of the semester. You have the normal distribution, the student's t-distribution, chi-square, and the F distribution. And again, we will touch on each of those. Our focus is going to be primarily on the normal and the student's t, because they're very connected to each other. But we'll talk about the others as well. And then you go into further detail with those in the Math 2401. Okay, so our focus today, that's kind of the broad view, but we're talking specifically about probability distributions, which is going to give us an insight into what should happen theoretically if everything worked the way it was supposed to. So we're going to move now and focus our attention on a binomial probability distribution. Okay, and so I'm going to start with defining what is the binomial probability distribution and that sort of thing. Okay, so hopefully if you've watched the video, some of this will sound familiar. Okay, but we're going to talk about the binomial probability distribution. If you're familiar with English, and I hope that you are, you probably know that the prefix bi, bi, bicycle, biped, binomial, bi means 2. Okay, so a binomial distribution, probability distribution, involves events that have 2 outcomes or can be reduced to 2 outcomes. And I'll explain that further as we go. Okay, so a probability distribution involves events, experiments that have 2 outcomes or they can be reduced to 2 outcomes. For example, The one that we just looked at, when you flip a coin, there are two outcomes. You can either get a head or a tail. When a baby is born, biologically, that baby is either going to be a boy or a girl. Again, two outcomes. Any kind of game or sport, whether it's a board game or an athletic event like basketball, baseball, soccer, whatever, somebody's going to win and somebody's going to lose. Again, two events. If you're checking blood pressure, if you're in the nursing field and you're checking blood pressure, or even for your own personal knowledge, blood pressure could be classified as you have a normal blood pressure or you have an abnormal blood pressure. Even when they're thinking about some kind of, you're thinking about some kind of medical treatment, whether, you know, it's a new drug or some kind of new, maybe radiation or chemotherapy or something other like that, we can talk about whether that treatment is effective. Does it work? Or is it ineffective? Again, think about probably something you could relate to right now with that would be the COVID vaccines. You know, are they effective or ineffective? Even something like rolling a die would be an example of where we can reduce the outcomes to two outcomes. Okay, because normally when you roll a die, there are 6 events. But if I focus on what I want, let's say I want to roll a 5, and then I can group everything else together as not 5. So I can reduce it to 2 events. I either get what I want or I don't. Taking a multiple choice test. Typically with multiple choice, you'll have 4 to 5 answers. And so you can reduce that to whether you choose the correct answer or the incorrect answer. So there are some events, and sometimes you may have to stop and think about it. Could that event be reduced to 2 outcomes? Again, such that you get what you want or you don't. Okay, so there's some examples of binomial probability distributions. There are 4 conditions that must be met in order for you to say, this is a binomial experiment and I can create a binomial probability distribution. Okay, so let's talk about those 4 conditions. Okay, so here are our conditions. First, you have to have what they call a fixed number of trials. And we represent that number of trials with a lowercase n. Okay, a fixed number of trials. How many times are you going to do this thing? Again, if we're thinking about the example of flipping a coin, how many times are you going to flip it? Are you going to do it 5 times or 10 times or 20 times or 100 times? That becomes your fixed number of trials. In a sense, it becomes your sample size because that's going to tell you how many results you're going to have. Okay, so you have to have a fixed number of trials. Again, to be a binomial, you have to have 2 outcomes only. Heads, tails, boy, girl, 5, not 5. You have to have 2 outcomes. They classify those 2 outcomes you either have success, they call it a success. Success means that you get what you want. Now, just because it's called a success doesn't necessarily mean it has to be a positive thing. You know, maybe my success is I want to know the number of games that the Atlanta Braves lose. Well, losing's not really a positive thing. But in this context, if that's what I've defined as what I want to look at as a loss, that becomes my success. So just because it's called a success doesn't mean that it has to be a positive event. Okay? The notation for success, we use a lowercase p, represents the probability of success. Okay, a lowercase p represents the probability of success that is determined theoretically. Again, the idea of flipping that coin. If our goal is to figure out the probability that they flip a head, that would be 1 out of 2. So the probability of success would be 1/2. On the flip side of that, the opposite of a success would be a failure. A failure, you do not get what you want. Okay, so they call the terminologies you may see are success and failure. Again, a probability of a success is denoted by P, and success means you get what you want. Failure implies you don't get what you want. It didn't work. And it is represented by a lowercase q. Okay, that's the probability of failure. And there's a formula for calculating Q. It is 1 minus P. Remember, 1 is the probability that something's going to happen, minus the probability of success. Whatever remains is your probability of failure. Okay. Third condition is that the outcome of each trial is what we call independent. Okay, and that's probably kind of a new word. You may not have seen that word before. Here's what that means. Again, thinking about it in the context of flipping a coin. Okay, I flip the coin the first time, I get a head. The fact that I got a head on the first flip in no way should affect whether I'm going to flip a head on the second time, or the third time, or the fourth time. Okay, whatever happens first doesn't affect what happens second or third or fourth or fifth. And that's what it means to be independent. We're flipping the same coin, we don't change coins. Okay. If you want to think about it like drawing cards out of a deck. The idea here would be that if I let Raphael draw the first card, he's going to draw it and look at it, and he's going to put it back in the deck. Okay, so that I still have 52 cards in my hand. Then I'm going to walk over to Matthew and I'm going to let Matthew draw. Okay, still from the 52 cards. He's going to draw a card, look at it, put it back. Okay, then I still got 52 cards in my hand. I'll walk to Jennifer and let Jennifer draw. Okay, because I'm not changing the makeup of the deck, every time I'm letting someone draw, I have 52 cards. They're independent. Now to contrast that, If I let Raphael keep his card when he draws the first one, I now only have 51 cards in my deck. So the chance of Matthew getting a particular thing is going to change. Because when he draws, he's only drawing out of the 51 cards. So he draws, he gets to keep his card, so now I only got 50. And I go to Jennifer, and let Jennifer draw. Her chances of getting the card that she wants is going to be different because now I only got 50 cards. It's a matter of, are you putting it back or not putting it back? With replacement, without replacement. With replacement makes it independent because you're keeping the deck or your objects all the same, quantity the same. But if you don't put it back without replacement, then it changes, and that's a problem in terms of a binomial. Now follow me? All right, the last one, the last condition says that the probability of success is constant from trial to trial. Okay, so again, the idea of flipping the coin, we're flipping the same coin over and over and over and over again. We're not changing coins midstream. They're putting the cards back into the deck. Okay, so that I have 52 cards each time they draw. So the probability of success doesn't change from problem to problem.
So are these just the rules for the binomial?
Those are the conditions. You have to meet all four of those things in order, and we're going to look at it in just a minute in an example. But you have to meet all four of those things in order to say this is a binomial experiment and we can apply the binomial distribution. If you don't meet those conditions, then you can't use the binomial distribution. You have to do something else.
Aren't 3 and 4
3 and 4 are kind of the same, but they delineate them out different, state them separate. Okay, so let's first look at this idea of meeting the conditions, okay? And we're going to do it a couple of times because we're going to look at some examples together. Okay, so here's our first scenario. A student, or let's say you, are going to take a 10-question true-false exam, and you forgot to study. So you're going to guess on each question. Okay, that's our scenario, and we want to decide, is that a binomial experiment? Does it meet the conditions of our binomial? So the first condition is, do you have a fixed number of trials? Yes. How many do I have? I have 10 because it says I'm going to take a 10-question test. So I have a fixed number of trials. I'll put a check mark, and N is 10. Okay, do we have, the second condition is you can only have 2 outcomes. In this scenario, do you only have 2 outcomes? What are they? True or false. So we have 2 outcomes. Okay, true or false. We'll have to define our success in a minute. Okay, if you're guessing on each question, does the answer you put for question 1 affect your answer on question 2? Is it going to affect question 3? No, and so forth. So the trials are independent, okay, because what you answer on one doesn't affect the other. So it is independent. And then the last one is the probability of success from trial to trial is constant. So let's talk about what the probability of success would be here. And I have to read the next question to find out. The question is to find the probability of getting 4 out of the 10 correct. So really, in terms of our outcomes, they're thinking about you getting it correct or incorrect. Okay, still 2 outcomes. Okay, so I'm going to make a note up here that we're really thinking about correct and incorrect. But you could also think about it and talk about it in terms of true or false. So our probability, our success here is that we get the question correct is our success, which is represented by the lowercase p. And what would that be? What is your chance of getting the question correct? It's going to be 1/2, 1 out of 2. Because there's one way to get it right. You're either got to answer true or false. One of those is going to be correct. We don't know which one out of the 2 options. So it's 1 out of 2 or 0.5. Now, just as a side note, because we might need that information later, what would be our probability that it's incorrect, which would be our failure? That's Q, which is 1 minus P, which would in this case also be 1/2. But we've met the 4 conditions. We got a fixed number of trials, 10. We have probably 2 outcomes, correct or incorrect, or you can think true, false. They are independent because what you answer on the first one is not going to affect the second, third, fourth, fifth. And the probability that you get it correct is going to be 1/2 or 50% for each question because you only got 2 choices, true or false. Okay, so then we want to find the probability of getting 4 out of the 10 correct. Now, guys, there's a formula that can be used for this. It's very yucky. It's on the PowerPoint, but I suggest you ignore it because Minitab will do the work for you. It'll do the calculations for you, but you have to know how to interpret it. And you notice if you look at the other examples here, the first one says getting 4 out of the 10 correct. Then the second question says getting at least 7 correct. And the third one says getting more than 6 correct. So there's different phrasing. And the phrasing matters. Okay, because that kind of tells you how to solve the problem. And guys, it's different for each phrase. I do not expect you to memorize how to do it for each phrase. I don't even have it memorized. On the PowerPoint for the binomial distribution on slide 8, there is this lovely table that Miss Ralston created. Okay? You need to make this table your friend. For the Module 2 exam that we talked about earlier this morning, that's on March the 15th, you will take it here in the classroom so that you have access to Minitab. You will be allowed to have one 8.5 by 11 sheet of paper with notes on it. Front and back. One piece of paper, front and back, any notes you want to put on there. Miss Ralston says, make you a small version of this table.
Or can we just take that to the other side?
If you want to take it to the other side and take up the whole side, have at it. Put the table on the note sheet. I don't even have it memorized. If I'm working these problems, I've got that sheet right next to me. Do you understand what I'm saying? Okay, so I'm going to lay this off to the side. So I'll have it when I'm ready for it. And I'm going to add a little word here just for emphasis. The first question says, find the probability of getting 4, but I'm going to add the word exactly. 4 out of the 10. We got to go out to Minitab to do the calculations. Okay. So I've got Minitab opened. I'm sorry.
Because I was looking for it and like.
It's Minitab 19. Is the one that you should download to your personal computer. Using the license that's in D2L though, so you can get it for free. Okay, if you're in or on the desktop here in the classroom, okay, I'm getting there. On the desktop, you should see a green square with what looks like white bar graph or vertical bars. A green square with white vertical bars that looks like a bar graph. And it should say Minitab underneath. Do you see it on yours? Okay. Did you find it, Raphael?
Oh, yeah, I did. I'm just looking for the license.
Oh, you don't need it for the classroom.
Okay.
Classroom is okay. If you're going to download it to your personal computer, you do need the license, and I can show you where that is when we're finished. Okay. Are you okay, Jennifer? All right. So I've got Minitab up. Okay. So the first thing we have to do is we have to think about the number of successes we could have. Think about how many of those 10 questions could you get correct? I could get 10. Just 10?
Oh, you get like 10, 9, 8.
I could do 10, 9, 8, 7,
6, 5,
4, 3, 2, 1,
or
or none. Oh, okay, that's what I wanted to get to. Guys, you got to remember that when you're thinking about the number of successes here that you're going to put in, that's your X value. You have to number from 0 all the way up to N. You have to include 0 because there's a possibility you don't get any of them right. And so you have to tell the computer that. Okay, so in column 1 in Minitab, I labeled it number of successes, and we could have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10. So that technically there's 11 things that could happen because you have to include the probability or include the possibility you got none correct. So you put in the number of successes. And then Minitab is going to calculate the probability for each of those. So I'm going to go ahead and label it. Column 2 is going to be the probability of a success, which is your lowercase p. Okay, I'm going to walk you through the steps on Minitab, and then I'll write it down on our paper so you can make yourself some notes. Okay, we want to calculate. So I'm going up to the Calc menu at the top of the screen, and we're doing a probability distribution. So I want to calculate a probability distribution, and we're doing specifically a binomial. Okay, we're going to calculate a probability distribution, specifically a binomial. We do have to change the default here. The default is to do a cumulative probability, which means it's going to add the probabilities as they go. We don't want it to be cumulative. We want to look at individual probabilities. So I'm going to click the button next to just plain probability. Okay, I want just plain old everyday probability. I don't want it to be inversed, and I don't want it to be cumulative. So change it to probability. Okay, then it's going to ask you how many trials do you have. That's the N. We had 10 questions, so we have 10 trials. The event probability, they're asking you for the probability of success, which we already decided was 1/2 or 0.5. It's easier to enter it as a decimal in Minitab, so I've entered 0.5. And then it asked me, where's the data? Where is the number of successes? That's in column 1. The input column is column 1. And then I want it to store my responses in column 2, right next to it. Okay. So I want it to calculate individual probabilities for the 10 questions where I have a 50% chance of getting it correct. And my number of successes are in column 1, and I'm going to store my answers in column 2. And then I'm going to click OK. And Minitab is programmed with the yucky looking formula, and it calculates those probabilities and gives them to you. Okay. So then I'm going to go to my question, back to my question, and I'm going to get my table. Okay. So let me make you a few quick notes here. In terms of the command, we went calc, probability distribution, binomial. And then the other big piece that you got to remember there is that you want just plain flat out probability. The particular question that we're interested in at first says, find the probability of getting exactly 4 out of 10. So I'm going to look at my table that I've been told to put on my note sheet and look for the phrase exactly. Okay, it's the very first one. Okay, and then I'm going to scroll over to how I'm supposed to calculate or interpret that. You read the results directly from Minitab for the value of X. And in our case, the value of X is 4. Okay, so if we wrote this in symbols so you can kind of see how it all goes together, we would have the probability that X equals 4. And that's going to be a direct read from Minitab. Minitab has done all the calculations. I'm going to the C1 column and I'm going to find the value of 4. And I'm going to read the number next to it. And the number that's written there, or that Minitab has put out, is 0.205078. Now, your homeworks, your test may ask you to round. I typically think I ask, if I remember correctly, for 3 places. So if I'm going 3 places, 1, 2, 3, next door to that, the 4th place is a 0. It's not going to change the 5. So rounded to 3 places, this would be 0.205. Don't overthink it. The computer is doing all the calculations for you.
Can you show how to do the calculation in the second column again?
Okay. Are you okay with entering the number of successes? You go from 0 to whatever n is. Okay. At the very top of your screen, go to calc, probability distributions. It's near the bottom of the list. Then you want to choose binomial. Make sure you change it. You don't want cumulative probability. You want just plain probability. So click the button next to probability. Tell it the number of trials, which was 10, because you had 10 questions. Probability you got it correct, we decided was 0.5. Your input column is where your successes are located. That's C1. And then we're going to store in C2. And then click OK. You good, Nick?
Yep, thank you.
All right, now I've created the table for the scenario. I've worked the first question. I'm ready to do the second question. I don't have to go out and recalculate it again. I already have the table. Okay, I just got to know how to read or interpret that table. This question says, find the probability of getting at least 7. So in symbols, that would mean you got to remember how to interpret at least 7. At least 7 means you could have 7, so it could be equal, but it could also be more. So X is greater than or equal to 7. If you don't remember that, again, knowing that my key phrase is at least, I'm going to get to my table and I'm going to look for the phrase at least. And it even explains it that implies that you have X or more. So in this case, I would have 7 or more. Okay, so at least, there's my phrase. Read over. It says add the results from Minitab for X, X plus 1, all the way up to N. So in our case, that means we want to add the values for 7, 8, 9, and 10. Now, there are 2 ways to do that. One way is to use your trusty dusty calculator. Okay. And very carefully type in the numbers from Minitab for 7, 8, 9, and 10. So I would type 0.11788 plus 0.043 plus 0.009766 plus 0.000977. Okay, guys, if you're typing them in, please be extra careful. Okay, so we took the values, and again, I'll make you some notes here. We need to add probability of 7 plus probability of 8 plus probability of 9 plus probability of 10. And you can do that on your handheld calculator. And when I'm finished, I have 0.171876 when I add those 4 values together. Now again, thinking about rounding to 3 places, there's an 8 in the 4th place, which is going to bump the 1, so it'd be 172. Now, adding 4 numbers, probably not too bad, but if you had to add 10 or 12 numbers, that might be more difficult. So I'm going to show you a shortcut. If you have access to Minitab, like you have here, we've got the results inside Minitab. Okay, I'm going to show you a shortcut. You ready? I need the values for 7, 8, 9, and 10. So I've clicked on the value for 7. I'm going to hold the shift and arrow down to highlight the others that I need. So I've highlighted the 4 numbers that I need. I'm going to right click and I'm going to copy. And then I'm going to paste those that I need in column 3. And then I'm going to let Minitab do the adding for me. See, I just copied them from one column to another column. So I haven't had to type them in and maybe mistype them. So I've copied them. And then I simply want it to calculate column statistics. I want it to calculate the numbers in that column. And I want it to do the sum. I want it to add them up. in the values in column 3. And I get 0.171875. Okay. Still going to be 0.172. Guys, to me, that's a whole lot easier if you have access where you can copy and paste and let Minitab do the work. That way you don't have to worry about mistyping a number. Okay, we'll do another one because we got to get, I'm sorry.
We have like a lot of things that
Probably not. I try to keep it like, I haven't looked at the test paper recently, but I think I try to keep it to like a success of 20. So it's not going to be a huge amount. All right, so then let's go back and look at the third one here. It says find the probability of getting more than 6. Okay, so our key phrase in this particular problem is more than 6. So in symbols, when we say more than, that doesn't mean it could equal that number. So it's just the probability that X is greater than 6. Yeah, I think so. I didn't do that on purpose. Let me change the number from 6 to something else. Let's see, getting more than, let's do more than 3, just so I can actually do the problem. Okay, so I changed the problem. Probability of getting more than 3 correct would be X is greater than 3. So then again, I'm going over to my table. I'm looking for that key phrase, more than, okay? Probability of more than, add the results from Minitab for X plus 1, X plus 2, all the way up to N. Do not include the result for X because it can't be equal to X. So you don't include the X. So in this case, since I changed the question, we need the probability of 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. Okay, so we would have to add together 7 numbers. 7 numbers. I don't really want to do that on my calculator, but again, Minitab will let me do it. Okay, so I'm going out to Minitab. This time I want more than 3, which is the values for 4. Highlight the one next to 4. Hold down the shift key. It's just like copying in an Excel spreadsheet. Okay, highlight the ones you need. Right click. Maybe. Copy the cells. Paste them in another column. And then you calculate the column statistics and you want them to add. This time I'm using column, I want to do column 4. And it gives me the value of 0.828125. Okay, again, notice if you round to 3 places, 1 is in the 4th place. It's not going to bump the 8, so you get 0.828. All right, let's change scenarios. And we'll think about, again, is it a binomial? I want to go through that again with you. Okay, this one says, according to a recent survey, 5% of Americans are afraid of being alone in a house at night. If a random sample of 20 Americans is selected, find the probability that, and then it gives us several questions. Okay, so first of all, we got to make sure that this scenario is a binomial. So do you have a fixed number of trials. Okay, that's not the number of trials though. How many are we going to have? 20, because we're going to use a random sample of 20 Americans. So that's the number of trials. We're going to ask 20 people. Now, Raphael, do we have two outcomes? Okay, what are they? Okay, in this case, our outcomes, you're either afraid or not afraid to be home alone in the house at night. Okay, so you do have two outcomes. Is the fact that my sister, who actually is afraid to be at home alone at night, the fact that my sister is afraid to be at home alone at night affect whether I am or whether you are? No. So that makes the outcomes independent. And then let's think about what would be the probability that they're afraid is our success. And what's the probability for that this time? What's the probability they're afraid? No. It's not 1/2. It's actually 5%. See, this one tells you 5% of Americans, based on the study that they did, okay, are afraid. So my probability of being afraid is 5% or 0.05. And it's going to be the same from trial to trial because it doesn't affect, you know, what me or you or whoever is giving the answer. Okay, so for my X values, again, thinking about the number of successes, in this case, we're going to, again, you got to include 0 all the way up to 20. So I'm going back to Minitab. And I could use the same worksheet again, but to try to avoid confusion for you guys, I'm going to open up. Oh, nope, that's not what I want. I want to get a new worksheet. Okay, so my successes would be 0, 1, 2, 3. Oops.
How do you know what your success is going to be? Like, why can't it be not afraid?
Because if you look at the way the next few questions are worded, it says exactly 11 people are afraid to be alone at night. Okay, so the question is afraid to be alone. So your success is that they're afraid. So it depends on how the question is worded. And it could be worded so that not afraid would be the success. So you just have to pay attention to how the questions are worded. Okay, so we have to number our successes from 0 to 20. And then we're going to look at the probability of success. Again, in this case, probability that they're afraid. We got to let Minitab do the work. So we're going to calculate a probability distribution that is a binomial. We want straight probability. My number of trials are now 20. The event probability, which is the probability they're afraid based on the phrasing of the question, is 0.05. My input column is the success, and I want to store it in column 2, and it does all the work for me. So the first question says exactly 11. Okay, exactly 11 are afraid to be alone at night. Remember, with exactly, you're just reading it directly from the table, which on this table, probability that X equals 11 is 0.000000. So for all intents and purposes, you would not get exactly 11 people who are afraid to be alone at night. It's virtually telling you it's an impossible event. But then the second question, and again, I'm trying to give you an example of all the different options you might see. The second one says, at most 3. Okay, again, you got to think about what at most means. At most means it could be equal to 3, but it could also be less. So you're looking at less than or equal to 3. So I get my table. I look for the phrase at most, and it does tell you there it implies X or less. So we add the results from Minitab for 0, 1, 2, all the way up to X. So for this problem, that means we're going to add the probability of 0 plus probability of 1 plus probability of 2 plus the probability of 3. But again, we're going to let Minitab do the work for us. So I'm going to start, highlight 0, hold the shift key, and get 0, 1, 2, 3. Copy, paste, calculate, column statistics, and I'm doing column 3. Column 3, not column 4, thank you. And I get 0.984098. Okay, Minitab's doing all the work for you. Again, if you're asked to round to 3 places, the 0 is in the 4th place. It's not going to bump it, so it's 0.984. And then the last example, again, trying to make sure you have one of all types so you'll have it to reference. We want fewer than 8. Fewer than implies it's less than, but it can't be equal. So fewer than is simply like saying less than 8. So going back to my table, finding fewer than, it says add the results from Minitab for 0, 1, 2, all the way to X minus 1. Again, we don't include the result for X. So for us, that means we're going to do the probability of 0, probability of 1, probability of 2, probability of 3, 4, 5, 6, and 7. We do not include the 8. So again, I'm going to let Minitab do the work. I need 0 up to 7. So 0, 1, 2, 3, 4, 5, 6, 7. Copy, paste, calculate, column statistics. I'm in column 4 now. Okay. We actually get a value of 1, which means you would definitely get fewer than 8 people that are scared to be at home alone at night. Now, one other thing that we can do with these type problems with the binomial distribution, we can also find the mean and the standard deviation. Because remember, when we talked about descriptive statistics earlier in module 2, I told you that the mean and the standard deviation were the 2 most important descriptive statistics. because we use them in other calculations. And so we need to be able to find the mean and the standard deviation for a binomial distribution or for whatever distribution we're doing. So let's talk about that for a minute. It is basically a formula, guys, and that you plug and chug into. Okay, Minitab doesn't really do it for you, but all the information is given to you in the problem and you just plug it into the formula. So first, let me give you the formulas for the mean. And this is specifically for a binomial. The symbol for mean, remember, is the Greek letter mu. And it is n times p. So you're multiplying together the number of trials times the probability of success. So I'm still using the scenario about being afraid to be home alone at night. So we already decided that our n was 20 and that our probability of success was 0.05. Guys, don't make this difficult. It's simply a formula and you're going to plug and chug. So I would have the mean is 20 times 0.05. And I'm going to get my calculator and I'm going to do that. 20 times 0.05 is 1. So on average, 1 in 20 Americans are afraid to be home alone at night. Okay, then let's look at the formula for standard deviation. The formula for standard deviation, remember the symbol is the Greek letter sigma. It equals the square root of n times p times q. So you have the square root of the number of trials times the probability of success times the probability of failure. Now, again, you may have to calculate Q. Remember, Q is 1 minus P. So again, in the problem that we're considering, we have 20 Americans in our sample. The probability that they're afraid is 0.05. If the probability of afraid is 0.05, what's the probability they're not afraid? 0.95. So Q is 0.95. And again, guys, it becomes a plug and chug problem. So sigma, or the standard deviation, would be 20 times 0.05 times 0.95. Okay, I'm going to walk this out. So I'm going to do the multiplication under the radical first. So 20 times 0.05 times 0.95. Whoops, I did something wrong. 20 times 0.05 times 0.95 is 0.95. And then I'm going to square root it, which gives me approximately 0.97469. Again, you'll probably be asked to round it to 2 or 3 decimal places. Pay attention to the instructions. If it's 3, you have a 6 in the 4th place, which will bump the 4. So that becomes 0.975. So on average, 1 out of 20 Americans are going to be afraid of staying at home alone tonight with a standard deviation of about 9.5 or about one person. You could be off by about one person. So our range would be 0 to 2. All right, that finishes binomial. Next Monday, we talk about normal. We go to the continuous distribution. And I will see you then. Yes, I will.